We'll begin the discussion of inter-symbol interference and adaptive decision feedback equalization and equalization in general to combat inter-symbol interference in multipath fading channels, which we encounter both in Wi-Fi, WiMAX, and of course in cellular. A contribution by Falconer et al. In the EDU 2016 committee back in 2001. The paper was called Frequency Domain Equalization for the 2 through 11 gigahertz fixed band wireless systems, a tutorial. Falconer is an expert at in equalization with a long history of original contributions, especially in decision feedback equalization and so forth. And this is a very good paper that talks about all the alternatives in terms of equalization for WiMAX applications, but we refer you to this publication in terms of some more detail. Later on we'll show that due to the fact that OFDM uses the FFT and the OFDM symbol is cyclic in nature, we can use the cyclic prefix in order to combat inter-symbol interference, and we will use frequency domain equalization. But it's very important to go over where multipath comes about and how to combat it using adaptive filters in general. And then we'll move into the idea of using cyclic prefix and frequency domain equalization. Here we show basically the impulse response of a multipath channel. You'll notice that the impulse response is characterized by a precursor portion and a post-cursor portion. And due to multipath, we have the post-cursor extending in time. And usually this extension in time causes inter-symbol interference. If we look at the picture down here, we have a channel and filters. Usually we can combine the filters, for example the square root Nyquist pulse shaping filters, etc., and the channel into one impulse response that we show here as h of t. Imagine that we put in the symbols, which are pure impulses. These symbols have the data encoded in them, for example +1, -1 in a binary situation. And as this passes through the channel and filters combined with this impulse response, the output is a superposition of the impulse response of the individual symbols. And you'll notice that, for example, for the first symbol, its impulse response interferes into the second symbol and all the way almost into the third symbol, and the second symbol interferes into the third symbol, and so forth. And also there's an interference due to the precursor. The inter-symbol interference, of course, will degrade performance considerably and cause many errors. So we need to combat inter-symbol interference. Let's illustrate the concept of using an equalizer at the receiver in order to combat inter-symbol interference introduced by the channel. Again, we combine the filters with the channel and we show its impulse response. We have the symbols shown as ideal impulses going into the channel and filters and producing inter-symbol interference over here. And we have additive white Gaussian noise added, and the receiver receives the signal distorted by the channel and the additive white Gaussian noise, for example. And we have to equalize the signal. That is, we have to eliminate the inter-symbol interference and recover the original impulses with all the inter-symbol interference eliminated. Let's illustrate this. If, for example, the channel frequency response had this kind of characteristic, which is what we see for multipath fading channels, then if the equalizer frequency response was exactly the inverse of the channel frequency response, as shown over here, then the combined frequency response between the channel and the equalizing filter would have a flat response like this, actually being a constant 1. And in this case, we see that we can recover the original impulses and we have equalized the channel. So the concept of equalization is clear. The receiver needs to estimate the channel impulse response and invert it and multiply it times the input sequence in order to recover the data without inter-symbol interference. Of course, this is one way to look at things. A couple of issues can be highlighted here. One is the fact that as you see, the noise is added before the equalization. The equalizer, when you have deep fades, produces these enhancements, as you can see over here, and this is like a high pass situation where the noise is actually enhanced And this occurs precisely where the carriers are weak, so that one of the problems with this kind of equalizer is, of course, we have noise enhancement, but we do, of course, eliminate the inter-symbol interference. Now, this is an ideal situation. We'll show some of the issues involved in actual practical implementations of the receiver equalizers. What we want to do is look into the implications of deep fades on the structure of the equalizer and the complexity of the equalizer in order to combat the effect of these deep fades. Going back to our simple model of a multipath channel, we have the main ray plus a reflected ray. Of course, we have attenuation. There is a delay at the receiver between the main ray and reflected ray, which is the T sub D over here. And if we ignore the bulk delay, then S of t, of course, is just delta t, the main ray, plus alpha related to the attenuation, delta t minus td, the delay. Now, if we wanted to model this in the discrete time domain, we would have a discrete sequence x of n, which is the input, the signal over here, and it gets multiplied by alpha, and it gets delayed by, say, n samples. It's either the minus n representing a delay of n samples. And then it's added to the main signal to produce the output signal. So this is the discrete time domain model of the multipath effect shown here in the continuous time. So x of z is the z transform of x of n, and y of z, of course, the z transform of y of n. And this sort of models the multipath setup over here. In the discrete time domain, of course, we have associated with it, if it's modeling in fact, a continuous system, a sampling rate. This denotes the sampling rate by f of s. Then the inverse of the sampling rate is the time interval between samples, delta t. And the time delay would be n times delta t. So in fact, n is equal to the time delay divided by delta t, the interval between samples. And we will give an example of that. Of course, normally it's not an exact multiple, and this will be some kind of approximation. So given the time delay, we can figure, and the sampling rate, we know what n is, the delay, and we can model the multipath in the discrete time domain. Now, associated with this discrete time domain, of course, is the transfer function in the z domain, similar to the transfer function in the continuous domain, where we have h sub f, a function of frequency. We have here h sub z, and that's equal, of course, to yz over x of z, the output divided by the input. And if we write the output, y of z is equal to x of z plus alpha z to the minus nx of z, this is this situation here. And this, of course, reflecting the reflection of the multipath. Rearrange terms, and we get that the transfer function is 1 plus alpha z minus n. So this is the actual simple model of a single multipath reflection in a multipath type environment. And here we show, of course, in the continuous domain, the frequency response of the simple one reflection multipath. And recall that the spacing between the fades, delta f, was the inverse of the time delay. And the depth of the fades was related to the reflection, the attenuation over here. The less the attenuation, the greater the fade. Now what we're trying to do is to come up with the inverse model of the inverse channel so that we can equalize the multipath channel. Recall that we're trying to construct a filter that at the receiver that is the inverse of the channel, so that the combination of the channel and the equalizing filter is, of course, a constant in the frequency domain. And therefore we're trying to come up with a structure which is the inverse of the channel. So we're trying to come up with a structure which is the inverse of the channel, which is 1 plus alpha z to the minus n. If we look at this structure, we have a system in a discrete time domain where we have inputs x of n, or it's z transform x of z, and an output y of z of the z transform of y sub n. We take the output and we multiply it times minus alpha times and delay it by n samples. That's what z to the minus n means, and add it back to the input. What we're interested in is what is the transfer function, the z domain transfer function between the input and output. So we can write y sub z over here as x of z minus alpha z to the minus n y sub z. So we got y sub z times minus alpha times z to the minus n. and then we're adding it to x of z. So that's what we get over here. And if we rearrange terms and factor y of z and divide y of z by x of z, we get that the equalizer in fact has a z-domain transfer function which is equal to 1 over 1 plus alpha z to the minus n. So this particular structure has this z-domain characteristic, and if we take this equalizer, which is 1 over 1 plus alpha z to the minus n, and multiply it times the model of the multipath, as shown over here, so we take the multipath model times the equalizer transfer function, then they cancel each other out and we get 1. So theoretically, in an ideal situation, we will be able to, if we knew in fact at the receiver exactly what alpha was and how much delay we had, we can cancel out the effect of multipath. So to further model this, what we've done is set up a simulation in CAPSIM. In CAPSIM, we're showing actually a block which generates an impulse, and here of course we have the output being fed back by gain minus alpha times z to the minus n, and here we're actually setting up the delay and adding it back in, and this is all the discrete model, and then we're actually looking at the spectrum and impulse response at this point. This is basically a node block which just takes its inputs and forks it out, the same samples, to either an output and of course feeding it back into the input. This is the same structure as we have over here. Now we're using a sampling rate which is equal to 20 megahertz, so the time interval is 1 over 20 megahertz or 50 nanoseconds. So delta t is equal to 50 nanoseconds. We're dealing with a system where the delay is like 250 nanoseconds, so we have a multipath case where we have one ray which is delayed by 250 nanoseconds compared to the main ray. So for 250 nanoseconds divided by delta t, which is 50 nanoseconds, the time interval between discrete samples in our discrete time model, then the delay n is 5. So we can represent a delay of 250 nanoseconds with an actual delay of 5. So here we actually use a delay of n equals 5. So if we put in the impulse and actually look at the impulse response, we see this figure right here. So here we're showing the impulse response at this point. And what this illustrates is that the inverse channel has an impulse response which lasts quite a bit and over quite a extensive time period. So even though the delay was 250 nanoseconds, the impulse response decays and goes to 0 around 3.5 microseconds. And in order to model this impulse response, we require 70 taps. So if we want to model this impulse response with an FIR filter, for example, we would need 70 taps. That is 70 using 70 coefficients and a tap delay line in order to model this impulse response. If we look at the frequency response of this impulse response, we see this picture over here. And typically we'd have a two-sided spectrum over here, but we only show one side. And of course it's repeated. And you'll notice the peaks here corresponding to the points, delta f, which is related to 1 over the time delay, 250 nanoseconds over here. And this is, of course, exactly the inverse of the multipath channel. If you recall, we had the multipath channel with the dips and the fades. We've actually constructed a filter which, shows the exact inverse of that channel, and the overall response would be a constant. So this is the basic structure to model the equalizer at the receiver, and typically we would try to equalize the system using a tap delay line. So what we are showing is that when you have multipath, the impulse response of the inverse of the channel extends through quite a period of time. Like, for example, even for a delay of 250 nanoseconds, you have extends all the way to 3.5 microseconds using 70 taps. So to implement the impulse response of the equalizing filter, it would be very complex and require quite a number of taps. In this case, we would need 70 taps. So multipath has a number of implications. One is that multipath deep fades lead to long impulse responses, and therefore we need to model the impulse response using a large number of coefficients, and it takes a lot of computational complexity and resources in order to model that. That many taps are required, and we have high complexity. So let's try and find out a way to approach this problem so as to minimize the complexity. The method to use is of course using decision feedback equalizer. And in the case of a decision feedback equalizer, we use both a forward tap delay line that models the impulse response, the precursor of the impulse response, as we'll point out, and you use a feedback tap delay line to model the post-cursor part. This will actually reduce complexity. So what do we mean by decision feedback? So if this is the model of the channel, what we've been talking about, where we have the main path plus the delayed attenuated path, then that the receiver, in order to cancel out the effects of the multipath, we will need the inverse channel, which turns out to be this model. And this is what we'll be using, and this is what's behind the concept of a decision feedback equalizer, because we have a feedback through a tap delay line back into the input, and this is basically what we will use to cancel out the effects of the post cursor. And if we use such a structure, then we only need one tap and an attenuation versus a 70 tap FIR filter in order to eliminate the effects of that multipath. So here we show the architecture of a digital adaptive equalizer, and I'll explain this in a minute. Let's go back to our channel impulse response, and we'll notice that the channel impulse response has a precursor component and a post-cursor component. And we showed that for a multipath channel, the impulse response takes a long time to die off due to multipath, and the inverse channel impulse response for the equalizer actually can take quite a long time to die off due to the multipath effects. So the digital adaptive equalizer architecture is basically broken up into two sections. One is what we call the forward tap delay line here, and this models as much as the channel impulse response as it can using the computational resources we allocate to it. The remainder of the impulse response, which cannot be modeled by the forward tap delay line, is modeled by the decision feedback equalizer portion, which is the feedback that you see over here. And of course it's called decision feedback because it's based on actual decisions on the received symbols, and the decisions are actually fed back through a tap delay line and subtracted from the residual error from the forward tap delay line, and hopefully we've eliminated the intersymbol interference. At this point we pass it through the decision device and actually make decisions, for example in a binary case between +1 and -1, and we have the equalized symbols at this point. Now, one of the issues with this architecture is the fact that the forward tap delay line would need initial training in order to converge to the equalized symbols. So in this kind of architecture, typically the transmitter will send to the receiver a known sequence. That is a sequence known to the receiver. So initially when inputs are being received, the receiver knows exactly what was sent by the transmitter, and this switch here goes to this position. So actually this is connected to this position, and we're actually forming in the error between the estimations, the equalization of the input with the forward tap delay lines, and the difference with the training. Now if we take this error and we process this error in a minimum mean square sense, that is, we take this error and try to minimize it in a minimum mean square sense, and we're trying to minimize the distance between the training and the actual equalized symbols. We actually take this error back and feed it back and adjust these coefficients using, for example, a least mean squares filter, adaptive filter, and converge these weights such that the error is minimized at a minimum mean square between the training and the received. Then of course these symbols start to approach what the original symbols were sent, and that means that the channel is actually equalizing the input signal and eliminating intersymbol interference. However, we mentioned before that that's impossible to do using just the forward tap delay line. The fact is that unless we have an infinite number of taps here, or a very large number of taps, we will not be able to combat the effects of the post-cursor and intersymbol interference. The best way to do that, as we showed before, was to actually use the feedback tap delay lines and then form an estimation and subtract that out. So this is basically estimating the residual of the intersymbol interference. We subtract that out, make a decision, and we've equalized the channel. So initially we set the switch here to training. The transmitter sends a sequence that was basically modulated using a known training sequence to the receiver, and we minimize the mean square error using, say, the least mean squares adaptive filter algorithm, adjust these taps to minimize error as much as we can. After the training, we switch back here. We use the actual decisions on the partially equalized signal, feed those back through the decision feedback tap delay line, and we eliminate the post-cursor or residual intersymbol interference, and hopefully we've equalized the channel. This is a time domain adaptive equalizer, and we're showing this actually just for a real channel, not a complex channel. There are many variations on this architecture, for example, using fractionally spaced equalizers, which are immune to timing jitter, for example. There's a lot of analytical work that needs to go on and to see what the effect of the channel impulse response is, and of course the additive noise on the performance of this signal system, and of course its convergence behaviors and its overall complexity. There's another issue that we want to point out, and that is that in OFDM situations we're actually dealing with complex signals instead of real signals. And in complex signals, we'll have to actually equalize using complex taps. So here we're showing the received in-phase component Y of Z, Yi of Z, and the YQ of Z. And typically the channel in a complex situation will create interference between the in-phase component and the quadrature component. So the received signal has leakage from the in-phase into the quadrature component, from the quadrature component into the in-phase component. So the equalizer has to not only eliminate intersymbol interference in the in-phase component, it has to actually estimate the leakage or interference from the quadrature in-phase term into the, for example, a quadrature term, and eliminate that leakage, and of course the forward part to get the overall signal equalized. So in a complex scenario, of course, we got this structure where we have the cross elimination of leakage between the in-phase and quadrature phase components. So in the case of OFDM, you would actually have to implement the forward tap delay line and the decision feedback tap delay lines using complex operations. This type of architecture, of course, has been used quite a bit in equalizing signals in the digital modem arena, and also in, for example, early DSL, quite successfully. However, it is very complex, and it turns out that for OFDM, there's a different approach we can use in order to combat intersymbol interference. That is using the cyclic prefix, and that's the discussion that we'll get into shortly.